All right, let's continue on with some more questions from your BC Fall Semester Exam Review. Question number 38 asks us for what values of P will both series converge. So we've got two different series here. They both involve a P, and we want to find values that will make them both converge. Now the first example here, 1 over n to the 2p, this surely looks like a P series. And for a P series, that exponent 2p needs to be greater than 1 in order for the series to converge. And so if that's the case, then P needs to be greater than 1/2 in this particular series. For the second series, this one is in the form of a geometric series, which means that P over 2 should be less than 1. And if I solve that for P, then P is less than 2. So if P has to be greater than 1/2 and less than 2, those options match answer letter C, where it says that P is between 1/2 and 2. All right, question number 42. Which of the following converges for all real numbers x? Okay, this is a somewhat of an interval of convergence question, and that means that we need to do the ratio test. So I'm going to start with a ratio test on question A. We have x to the n over n. And I notice if I look at answer choices A, B, and C, they all have x to the n in the numerator and then different powers of n in the denominator. Like they look like P series times the x. So I'm going to work one of them as interval of convergence and see if we can't come up with an idea about all three of those. So R equals the limit as n goes to infinity of the n plus 1 term, which would be x to the n plus 1 over n plus 1 times the reciprocal of the nth term, which would give me n over x to the n. And we're going to absolute value that, and we want this to be less than 1. All right, so I'm going to do some simplifying. X to the n is going to divide out with the n plus 1, leaving x. And then the n and the n plus 1, those do not simplify. The x term we're going to bring out into the front, absolute value of x, times the limit as n goes to infinity of n over n plus 1. Well, that limit is, of course, 1. And so what I end up with is the absolute value of x less than 1. Now, this is only going to be true for particular values of x. This is not going to be true for all real numbers x. If you remember from class, the way we get one that's true for all real numbers is if this limit that we take here comes out to be 0. Because then if I'm multiplying by 0, then it's always less than 1, which means it's always going to be converging. So answer A is out. It does not converge for all x's. And if I think about doing the ratio test for n squared and n to the 1/2, the same thing is going to happen as happened with answer A, that I'm going to end up with a limit here of 1. Because these are all polynomials, I'm going to end up with an n to some exponent over n plus 1 to the same exponent, and we're going to have a limit of 1. And so that means that none of these three are going to converge for all real numbers x, only for certain ones when x is less than 1. So now let's go over and try answer D. Again, I'm going to do the ratio test. Limit as n goes to infinity. I'm going to do the n plus 1 term, e to the n plus 1, x to the n plus 1 over n plus 1 factorial times the reciprocal of the nth term, n factorial e to the n x to the n. And we want this to be less than 1. All right, I'm going to do some simplifying here. The n factorial is going to divide out with the factorial. X to the n divides those out, leaving x, and e to the n divides out here, leaving e. And if I bring my absolute value of x out to the front, then we're doing the limit as n goes to infinity. I took the x out to the front. All I have left is that e over n plus 1. Now, this is a little bit tricky because we see e, and I think we naturally want to think that's e to the x or e to the n there in the numerator, which would mean that this limit here would go to infinity because the numerator would be growing much faster than the denominator. However, this is just e in the numerator. It's just a constant over n plus 1. So the denominator is going to grow much faster, which gives us a limit that is 0. And so that's going to make it always less than 1, which means this is the one that converges for all x. Answer choice D. All right, question number 43. What are all values of x for which this series converges? Now, this certainly sounds, again, like an interval of convergence question, where normally we would use the ratio test, except in this case, this function right here is already in the form of a geometric series. And remember, the point of the ratio test is to treat other series like their geometric series as n goes to infinity. But this one's already set up that way. So I'm going to treat this like a geometric series. And what the geometric series says is that the common ratio, which is 2 over x squared plus 1, that part must be less than 1 in order for this to converge. Or actually, more accurately, the absolute value should be. Although my denominator here is always going to be positive because x squared is positive and then I'm adding 1 to it, so we don't really need the absolute values. I'll just take them off. So we need to solve this for x. I'm going to multiply x squared plus 1, so I get 2 less than x squared plus 1, which means x squared is greater than 1. And so that means if I square root both sides, it seems like maybe x greater than 1 would be the only answer. But remember, when we square root both sides, we need to consider the positive and the negative. And if we consider the negative, that's going to flip our inequality sign. And so really our answer here is x greater than 1 or x less than negative 1, which corresponds to answer D. All right, question number 45. Here we've got a generic series, a generic Taylor series. The sum of a sub n times x to the n is a Taylor series that converges to f of x for all real x. And it asks us, if that's true, then what is the derivative at 1? There's a couple ways that you could approach this question. If you're not really sure what to do, a lot of times a good idea is to generate a few terms of the series and see if that helps you out. Notice that n starts at 0, so if we generate some terms, we would have a sub 0, whatever that is, times x to the 0, plus a sub 1 times x to the 1, plus a sub 2 times x squared, plus a sub 3 times x cubed, and I think we get the idea, plus dot dot dot. So this converges to f of x. So if I find a derivative, this first term, x to the 0, is just 1, so this is a sub 0 times 1, which is going to be a constant, so that derivative is just 0. Plus a sub 1 times x, that derivative would be a sub 1. The next term, and this is where we really start to see what happens. If I take the derivative here, I get 2 times a sub 2 times x to the 1. And then in the next one, I get 3 times a sub 3 x squared plus dot, dot, dot. And we continue in the same manner. So that would be my derivative. And if we plug in 1, and we're plugging in 1 for x, then I end up with a sub 1 plus 2 times a sub 2 times 1 plus 3 times a sub 3 times 1, and it would continue on in that manner. And so this expression that we see here, that corresponds to answer D. What's happening here is we end up with n times a sub n, starting at 1 and going to infinity. Answer D. All right, next up is question number 50. And this question is asking which of the following statements are true, and the statements involve different variations on it converges absolutely or conditionally, neither conditionally nor absolutely, or it diverges. Now before we even start working on this, I want to talk about answer choice C. The series converges but neither conditionally nor absolutely. I notice here that this is an alternating series because we have this -1 to the n here in the numerator that makes it alternating, and that means that never would answer C be true. If it's going to converge, it has to be conditional or absolute. So answer C is out right off the bat. When we're checking for absolute or conditional convergence, sometimes it's maybe a little shortcut to check for absolute convergence first, because if we determine absolute convergence, then we know that the series converges and that it converges absolutely. If absolute convergence, if we check for absolute convergence and it doesn't converge, then we need to check for conditional convergence. But let's try absolute convergence first. What absolute convergence is when you take the positive version of the series without the -1, without the alternating part, so that would just be 1 over 1 plus the square root of n, as n equals 1 to infinity. Taking the positive version of this series, and we want to check this for convergence. Now what I have here is something very close to a p-series, and so we're going to use comparison to check it. And I want to compare to, oh sorry, I started writing what I was saying. We would compare to 1 over n to the 1/2, or 1 over the square root of n. And in this case, that is a p-series, and p equals 1/2, which is less than 1, and that means that my comparison here diverges. And we want, if we did, well, we're doing multiple choice here, so we can just kind of do the shortcut here, that when it's just polynomials, we can just kind of ignore this extra term here, the +1, treat it just like a 1 over square root of n, which would be into the 1/2, which means this is going to diverge. If we were doing this on free response, we would need to show our work and actually do a limit comparison. I can't do this by direct comparison because since my comparison diverges, this one would need to be bigger than the comparison series, and it is actually smaller because of the 1 plus the square root of n. So we would need to show limit comparison, but for multiple choice here, we know this diverges. So it is not absolute convergence, because if it was absolute, then the positive version of the series would have to converge. To check for conditional convergence, we've got an alternating series here, and we just need to check to see if it converges by the alternating series test. And what that test says is that if we take the limit as n goes to infinity of 1 over 1 plus the square root of n, that has to equal 0. And this does, so check. And then we also need to make sure that the terms are decreasing. So if I have 1 over 1 plus the square root of n and I compare it to 1 over 1 plus the square root of n plus 1, is that n plus 1 term going to be smaller? And yes, it will be smaller because the denominator is bigger and that makes the fraction smaller. Therefore, our terms are decreasing, and so our series does converge by the alternating series test, which makes it conditionally convergent, and answer B is the correct answer. All right, question number 51. It's the last one we're going to do here. Which of the following series converge? And we've got 3 series here to consider. Our first series, n over n plus 2, if we take the limit as n goes to infinity of n over n plus 2, that limit is equal to 1. These terms do not go to 0. 1 is not 0, and therefore this one diverges by the nth term test. Not that you have to write that on multiple choice, but just to remind you what I'm doing here. All right, answer choice number 2. Got a weird little thing here in this cosine n pi. N starts at 1, and let's just consider that part of the series here. We would get cosine of 1 pi over 1 plus cosine of 2 pi over 2 plus cosine of 3 pi over 3, and so on. Cosine of pi is -1, cosine of 2 pi is +1, cosine of 3 pi, -1, 4 pi would be +1. So this is just one of those different means of saying this is an alternating series. Cosine n pi is just going to go back and forth between -1 and 1, making this an alternating series. And in fact, it is the alternating harmonic series because it's just over n, alternating harmonic, and that series diverges. I'm sorry, it's late. That series, alternating harmonic series, converges. The last one, number 3, is the harmonic series, which diverges. Duh. Harmonic series diverges. Okay, and so we have the first one diverging and the last one diverging. The only one that's converging there is number 2, which gives us answer B.